Hello and welcome to Database Management Systems. I'm Jovita Christie, and in this video, I'm going to explain two more concurrency control schemes in transaction management, which are validation-based scheme and multi-version scheme. In my previous video, I've already explained the other two schemes, so you can watch that for getting to know more about concurrency control techniques. So let's begin. The first technique we're going to see is the validation-based protocol, and it is also known as an optimistic concurrency control. In this, it requires that each transaction TI executes in 2 or 3 different phases in its lifetime, depending on whether it is a read-only or an update transaction. So if it is a read-only transaction, then it's only going to read data and not write data. So then it would not go through all the phases, all the 3 phases. So it would go through only 2 phases. But if it is a transaction that needs to update or write any data item, then it will have 3 phases. The phases are, the first phase is known as the read phase. During this phase, the system executes the transaction TI, and the transaction TI reads the values of the various data items and then stores them in variables that are local to TI. So all the data items are read and they are stored in temporary variables, which are not updated or modified into the system because they are local variables. It performs all write operations on the temporary local variables without updates to the actual database. So the actual database is not updated, but still all the write operations are performed on the temporary local variables. And this is the read phase. So it is known as an optimistic concurrency control scheme because in this, the transaction is already hopeful that whatever it is writing is definitely going to get updated and it's definitely going to work. So even before performing any of the tests, the transaction will simply perform all its write operations, but on temporary local variables. And then there are some tests performed. So that brings us to the next phase. This phase is known as the validation phase. In this phase, a validation test is applied to the transaction TI, and I'm going to tell you what that test is after a little while. And if the transaction passes the validation test, then TI is allowed to proceed to the write phase without violating any serializability problems. And if the transaction fails the validation test, then the system aborts the transaction. So it's a very simple validation phase. There's a validation test. If the transaction passes the validation test, it is allowed to move to the write phase, which is the next phase. And if the transaction fails the validation test, then the system is going to abort the transaction. Now let's see what the validation test is. The validation test requires 3 things. The first thing is the timestamp of the transaction when it started. So start TI is the time when the transaction started its execution. It also needs validation TI, which is the time when TI finished its read phase and started its validation phase. And it also requires a finish TI, which is the time when the transaction finished its write phase. So there are 3 things required in the validation test. One is the start TI, which tells you when the transaction started. Validation TI, which tells you when the transaction finished the read phase and started the validation phase. And finish TI tells you when the transaction finished write phase. Now, other than this, in the validation test for transaction TI, you also require for all transactions TK. Now, this is where we are actually applying the scheme of validation. So here we are comparing all transactions TK with a timestamp less than the timestamp of TI. So the timestamp, when we say timestamp TK less than timestamp of TI, which means we are talking about all the transactions that entered into the system before transaction Ti. So if there's a transaction Ti which is having a timestamp of 20, then all the transactions that have a timestamp of less than 20 will be transactions Tk. And for that, we need to check two conditions. The first condition is that the finish Tk, that means the finish time of all the transactions which have arrived into the system before Ti must be less than the start Ti. That means Ti should start its read phase only after the other transactions that arrived before it have finished their write phase. So since Tk completes its execution before Ti started, obviously the serializability order is maintained because Ti is going to wait for other transactions that arrived before it to finish their work first. And the second point is that the set of data items written by Tk does not intersect with the set of data items read by Ti. And Tk completes, so let me just explain that first. The set of data items written by Tk. So if Tk, and remember Tk is not one transaction, Tk can be many transactions. So all these transactions, if they are updating certain set of data items, for example, A, B, C, D, then this set should not intersect with the set of data items read by Ti, which means Ti should not be reading A, B, C, D. It can read other data items, but not A, B, C, D, which have been written by Tk. And Tk completes its write phase before Ti starts its validation phase. So this is the next point where start of Ti must be less than finish of Tk, and it must be less than validation of Ti. So Ti can start before Tk is finishing its write phase, but the validation phase of Ti must start only after Tk, all the Tk transactions have finished writing whatever they need to write. So this would ensure that the writes of Tk and Ti do not overlap. If it overlaps, all sorts of inconsistencies will be caused. Since the writes of Tk do not affect the read of Ti, and since Ti cannot affect the read of Tk, this is because both of them are working on different data items. The data items that Tk is writing are not the data items that Ti is reading, so it can perform that simultaneously. So, and since Ti cannot affect the read of Tk, the serializability order is again maintained. Now, this brings us to the write phase, which is the last phase in the validation-based protocol. In this, if the validation test succeeds for transaction Ti, then the temporary local variables that hold the results of any write operations performed by Ti are copied to the database. And read-only transactions omit this phase, obviously, because it's a write phase. So the transactions that only needed to read a data item and not write would not have to go through the write phase. But what happens in the write phase is, if you remember, I told you in the read phase that the transaction already made all the changes to its local variables, not to the database, but to temporary local variables. So all these changes, if the transaction happens to get into the write phase, and remember that the transaction can only reach the write phase after passing the validation test and after finishing the validation phase. So after that phase is over, when the transaction gets to write phase, then all the temporary local variables where the transaction's data was stored and all the results are there, those operations, those variables are then copied to the database. And that's when you can say that the transaction is finally over. So that's what the validation based protocol looks like. The second type of protocol that I'm going to explain in this video is a multi-version timestamp scheme. In this, each data item queue, there is a sequence of versions associated. That means For one data item, there are several copies. So there's a Q1, Q2, QM, so many copies of one data item Q. Each version QK contains 3 fields. So now each data item has different versions, and each version QK, where K can be anything from 1, 2, 3 up to M, it contains number one, content, which is the value of the version QK. So it's not necessary that each version of Q will have the same value. So content is the value of the version. Then there's also a timestamp, which is a W timestamp of QK, which is the timestamp of the transaction that created the version QK. So whichever transaction created the version QK of the data item Q, its timestamp will be known as the W timestamp of QK. And lastly, there's also an R timestamp of QK, which is the largest timestamp of any transaction that successfully read the version QK. So this is the version QK, and any transaction that managed to successfully read this version, that transactions, if it is having the largest timestamp. So if there are 10 transactions reading QK, and out of that, the largest timestamp is of a transaction having timestamp 20. Then the R timestamp of that particular version of Q, which is QK, will be equal to 20. Now how the scheme is applied, we are going to see that. So suppose there is a transaction Ti which issues a read Q operation or a write Q operation. Then let us also use QK to denote the version of Q whose write timestamp is the largest write timestamp less than or equal to timestamp of Ti. So we have several versions of Q. Remember that we have a data item Q, but we have many versions of Q. From there, we are going to pick the version of Q whose write timestamp is the largest write timestamp, but it is less than the timestamp of Ti. So it shouldn't be a timestamp greater than Ti, but less than Ti, which means we are making sure that we are picking a version of Q that has been updated by a transaction that appeared just before Ti. So that way we can make sure that it's a data item that was written by a transaction that appeared just before Ti. Now, the first rule that applies is if the transaction Ti issues a read queue, so this is about just reading the data item, then the value returned is the content of version QK. So if the transaction Ti only wants to read the data item Q, then all that is done is the content of QK, which is the version that we have picked, that content is simply returned because there is no need to write anything. Now the second part is if the transaction Ti wants to issue a write queue. So this is where we need to think about it. Read queue is simple. You just pick the transaction, pick the version of data item Q with the largest write timestamp less than or equal to timestamp of Ti, and then just return its content. But if it is write queue, then you need to check several things. The first thing you need to check is if the timestamp of T is less than the R timestamp of QK. Remember that the R timestamp of QK is what I explained to you a little while ago. If you have forgotten it, please review that once again and then come back here. So the R timestamp, the timestamp of Ti must be less than the R timestamp of QK. On the other hand, if the timestamp of Ti is equal to the W timestamp of QK, which means the write timestamp of QK, then the system overwrites the contents of QK. So these are the things you need to check. The first thing is if the timestamp of Ti is less than the R timestamp of QK, then the system rolls back Ti, because that means Ti is not supposed to modify that particular version of the data item Q. And so that's why the system will simply roll back TI. The second thing is if TI is having a timestamp which is equal to the W timestamp of QK, then the system will overwrite the content of QK, which means the system is allowing TI to modify the data item QK version. And otherwise, the third possibility is if the timestamp of TI is greater than the R timestamp of QK, then in this case, the system will create a new version of Q. A new version of Q because TI is a transaction that has appeared after all the transactions that have modified Q have finished. So there is no need for TI to wait. It needs to create a new version of the data item Q and start working on it. So this is how the multi-version timestamp-based scheme works. And that's it for concurrency control and for this video. I'll see you in the next one. Thank you for watching.